One way that we can represent electromagnetic waves is having the electric field in one direction. In this case, we've got it in the y direction, and the magnetic field in the z direction. So they're 90 degrees apart from each other. This may or may not happen at 90 degrees, but in this case we're doing an idealized situation. And the direction of motion is along the x-axis. Now, let's take a look at just one section, and we're going to look at the electric field and determine how we can use Faraday's law to come up with a relationship between the electric field and the magnetic field. So remember from Faraday's law, it's the integral, line integral, of the electric field dot differential length is equal to the negative of the change in flux of the magnetic field with respect to time. Well, let's break this apart a little bit. First we'll start with the flux, and the flux is just equal to the change in the magnetic field times the area. Well, the area is just delta dx times delta y. And for the electric field, integrating around this section here, not this square, then we have 0 magnitude here, this part, times our length dx, cosine of 90, then we're going to have plus, and we're going to have an E plus a little dE. We're going to extend it up here a little bit above. And that's going to be times delta y at a cosine of 0 degrees. Now we're going to subtract this little section here, and that's just going to be E dx cosine of 90 degrees and then we're going to have this back section, and that's going to be minus E delta y and a cosine of 90 degrees. Yes, or no, I'm sorry, 0 degrees. 0 degrees. And that's going to have to equal our change in magnetic field. Well, this term is going to go away, and this term is going to go away. So I'm going to have E plus dE. Cosine of 0 is just 1, so I'm going to have delta y minus E delta y is equal to negative change in magnetic field in time dx delta y. And notice that the delta y's are going to go away. I'm going to have E minus E, So I'm going to just have delta E, we'll put it in delta Y here just to write it out a little bit, equals dB dt dx delta y, and I can take the delta y's out, I can move the delta x over to the other side, and now I get a partial differential with respect to x. So the partial differential of the electric field with respect to the differential x is equal to the negative partial differential of the magnetic field with respect to time. So this is one relationship. Now let's look at it in terms of Amperes law. Here I have no enclosed constant currents, so Amperes law is going to be line integral of the magnetic field times differential length, or dot differential length, is equal to mu naught epsilon naught d electric field electric field density or electric field flux dt. And for this line integral, I'm going to have what looks very similar here, except I'm going to be going along this line. So I'm going to have b delta z cosine of 0 degrees and that's for this part up here. And then I'm going to have plus, oh I'm sorry, that's this part right here, that part. Now I'm going to do this part on that one edge. So it's going to be plus b dx cosine of 90 minus, I'm going to have this little extra section there, b plus dB delta z cosine of 0 degrees minus 0 times dx cosine of 90 degrees. And that's going to equal, and I'm going to convert this into mu naught epsilon naught d electric field dt, and then I'm going to have dx delta z. So this term, second term, is going to go away, last term is going to go away, and I'm going to have b delta z minus b plus dB delta z is equal to mu naught epsilon naught differential electric field with respect to time dx delta z. Well, this first part is going to go away, and I'm going to be left with the magnetic fields are going to go away, and I'm going to only be left with a differential electric field, or I'm sorry, differential magnetic field, and that's negative, is equal to mu naught epsilon naught differential electric field with respect to time times dx, and I'm going to get a partial derivative of the magnetic field with respect to x is equal to negative mu naught epsilon naught partial differential of the electric field with respect to t. So these two equations are used to define and relate the magnetic field to the electric field. Our next presentation, we're going to see how we can use these to come up with a very useful relationship.